De Moivre's theorem.
I believe this is French, and it's pronounced De Moivre's theorem. But if you want to call it, if you want to show where you're from and say De Moivre's theorem,
we're going to talk about De Moivre's.
Yeah. So we first want to maybe remind ourselves about graphing complex numbers. When we talk about complex numbers, instead of having the x and the y axis, we have a real axis and an imaginary axis.
Fake.
Yeah, you might call it fake. It's imaginary, and
Is it like my imaginary friend? Hello,
No.
Mr. Bobo Skins. How are you today?
No,
I'm fine, thank you.
No, it's not like that at all. So what you do is you take the real part of the complex number, because remember, complex numbers are anything of the form a plus bi.
And every number is a complex number.
Is, because, for example, you would have the number 2, and that's really got an imaginary part to it. The imaginary part is just 0. So if we're talking about graphing complex numbers, you take the real...
hold on. I got an idea.
Oh, okay.
We could do this exactly like we graph x and y numbers.
Yeah, except for what is our x?
The first number.
Okay.
Just like x, y.
Okay, and what's our y?
The second number, including the sign.
Assuming that it's in the right order.
Right. Well, yes. Okay. You got me on that one. The real
part is the x, and the imaginary part is the negative 2.
Right.
So we go right 1 and then down 2.
There it is right there.
And that is the complex point, 1 minus 2i.
Right.
So that's just to get us like all on the same page. We're going to do all kinds of stuff with complex numbers, but we're going to have some familiarity to like vectors and polar equations.
Right. We're still going to work some of that stuff too.
It's all going to look similar.
But the graphing part is, you've already done this kind of graphing. It's the same setup as long as you're in a plus bi form.
Yeah, definitely. So let's get on to something else.
Okay, let's do.
Okay. We've got some definitions to talk about real quick before we dive into some more examples.
It's always good to have a definition or two.
Yeah, when we see absolute value bars around, we tend to call complex numbers z for whatever reason. And when you see absolute value bars, that's called the modulus of a complex number.
It's a really fancy word for distance.
Yeah, because we're saying basically if we plot this point in the complex plane, a plus bi, then we're finding that distance from 0 to that point. Kind of like a radius, right? Or kind of like a hypotenuse. Right. We've been doing this situation like the entire chapter, just with vectors, with polar coordinates.
The whole
and equations.
time. This should not be a new deal. And with vectors, we recognized length the exact same way with the absolute value bars. Right. So this is not even new notation.
Yeah. So that's just what we're saying here. And look, we've got this picture. Even we've got the real axis, imaginary axis. Here's some point a plus bi, and r right here. That's what the modulus is. It's the length of that line to get out to the point. Right. So that's our first definition we want to look at. And now we want to look at the definition for trigonometric form of a complex number.
Which can be super handy, actually,
yeah,
as it turns out.
There's some things that you can do with it that you can't do as easily if you have a complex number.
Right.
So the trigonometric form of a complex number is r times cosine theta plus I sine theta. And if you look back at the picture that was just up, it should kind of make sense, and also with what we've done with vectors and things, that the cosine theta, the r cosine theta, that's your x value.
Every single time it's your x value. And it has been since we started talking about trig.
Yes, and r sine theta, that's your y, but our y values in the complex plane have an I. So that's why this I is right here and only right there. Right. Okay, because this is giving, the r cosine theta gives us our real part, the r sine theta gives us our imaginary part. Right. And these relationships here, like you just said.
What'd you mark out modulus for?
I didn't mean to.
Why
I just got carried away. Sorry. These are all very familiar. This is what we've been doing. And so to figure out what this theta is, just like we've been doing, we have to do inverse tangent. And
that's usually the best way to go, because you will know A and B.
Yeah.
There's other ways to find it, but usually if you do that arctan, that's the ideal way.
Yeah. And so they call theta the argument of z. We don't necessarily say that a whole lot.
Why wouldn't you say that?
I mean, I don't think.
Why are you arguing with me?
Never mind. But here's the deal. We're gonna find some trigonometric forms of complex numbers.
Let's do it.
And so 2 plus 2i, we can easily figure out what the modulus of that is. right? 2 squared
Square
plus
root
2
of
squared.
4 plus 4. Square root of 8, 2 square roots of 2.
Right.
Or
Okay.
square root of 8 would be acceptable.
Yeah.
We're not grading reducing radicals with this particular item.
Right. So then the tricky part may be to find theta. And what's important is that whether you draw it out or whether you're just thinking it, you need to know what quadrant 2 plus 2i is
Yeah,
in.
we've got to get the right theta. And if you don't know the right quadrant, you won't get the right theta.
Right. Since this is in the first quadrant, our calculator, if we use our calculator, we actually don't have to on this one.
Nope, not on this one.
But if we use our calculator, it will actually tell us the correct angle because we're in the first quadrant. Any other quadrant, we have to do a little bit more work.
Correct.
And one way, if you're looking at this, and we just said you don't necessarily have to use your calculator, if you don't recognize that, when you're doing inverse tangent, if you put it in degree mode, even if we may want this in radians, right? If you just test it out in degree mode, and this should come back and tell you, hey, dude, that's 45 degrees.
45, yep.
Hey, that was on our unit circle. And if you think about it, 2 over 2 cancels out and gives you 1, which is 45 degrees.
What angle gives you a tangent of 1?
Right, and so 45 degrees in radians is pi over 4. We'd really rather have radians, so let's just set this up. Looking at z equals that formula up above, r, which is 2 square roots of 2 or square root of 8, and then you put cosine of pi over 4 plus I sine pi over 4. This is the trigonometric form, and all it does is it tells us the radius and angle instead of telling us like an x and a y.
Right.
Okay, it's no big deal.
So
hey, Mr. Bulwer.
Dip down in, Mr. Bulwer, and you can be in. Say hi to the children.
Yeah.
Here, we'll pause it real quick.
No. Oh.
So part B, now this one we're not going to be able to use the unit circle for because 4 over 7, that's not a ratio
It's no deal there.
that we see on the unit circle.
Yeah.
So start off here finding the modulus. Remember to put that negative in parentheses.
Yeah, if you don't put it in parentheses, you're going to get an imaginary number, and guess what? This isn't where that's supposed to happen.
Right.
Imaginary number happens in a minute, not right
but
now.
Your modulus should not be imaginary because it's a distance.
Yeah, it's a distance. Like if you get in your car and you drive, your odometer goes forward. That's what we're doing here. Doesn't matter what direction you go, odometer's moving forward.
Right on. 16 plus 49.
362.
Could you be for real? Just for a moment. 16 plus 49. I believe it's 65.
16 plus 49. Whoops. I'm just going to double check because 16 plus 49.
This is important.
We got to get to 65.
Okay, so
we
the
got to get that
modulus,
one
the
right.
r in our formula is square root of 65. Now, I want to think about where in the world is 4 negative 7? Well,
4
down here, right?
negative 7, yes.
Okay, and so our calculator is going to give us this angle, and so if we want the legit angle, like the real one, then we would do 2 pi minus that angle because it's over here.
Right.
We're going almost all the way around to right there. So
how short of 2 pi are we? That's what we want to know.
Right, and because we know this isn't on the unit circle, I'm going to put this in radian mode, and that means it's going to look kind of funny because it's going to give us a decimal. Weird. And our calculator is going to tell us it's negative
1.052.
Okay. And so what we have to do, you have to make sure that you realize this. We're doing 2 pi minus that number, and if you do 2 pi minus second answer, it's not going to do what you want if that negative is in there.
7.3348. 7.335. 3.
What is 2 pi?
2 pi is...
you just did what I told them not to do.
Dang it!
You minus the negative. I was like, that's bigger than 2 pi.
What I meant to say was...
This is an example of what happens if you do 2 pi minus a negative 1.052.
Why would you say that about me? 5.232.
That right there. That is our theta for the problem.
You wounded me, why?
I'm sorry.
You offended me greatly.
5.232 cosine, that's not where that
goes. No. Square root 65.
No.
Why would you do that? There you go. Now get your 5.232 in there. And usually we want to go 3 decimal places. Every now and then 1 more or so, but we'll let you know what that is. 3 is a pretty safe place.
Yeah. There you go. We just plugged in r and theta once we had it. That's our answer right there.
Yep. And if you do this correctly, if you distribute all of this out.
It should
come back to 4 minus 7.
It should come back to 4 minus 7i.
Way to copy me. That's a great job.
True story.
Yes, true indeed. Okay.
So, and incidentally, that's what example 3 is about.
Shut the front door.
No. Write the complex number in standard form. All we have to do is distribute.
Hey, by the way,
evaluate.
This one should have no decimals for your answer here because
this 30
is on the unit
is
circle.
Pretty clearly on the unit circle. And so you go to cosine at 30, that would be square root of 3 over 2.
Yep, square root of 3 over 2.
So cosine of 30 is square root of 3 over 2. I'm doing it this way. You could do it a slightly different way if you wanted to. I just thought I'd figure out what cosine and sine were. Yeah, 1/2. That's right. Sine 30 is 1/2. Now we want to distribute the 3, so that's 3 square roots of 3 over 2 minus 3/2 i, because typically we put the I at the end.
Usually, or you could also see it as 3i over 2.
Yes, you could. You could do that. Yeah. You could say that's 3i.
I doesn't usually go in the front, though.
I don't know. Sometimes
I don't either. That's
yeah,
a good one.
Yeah, totally.
I think this example's over.
Yeah. Now this is a fun one. De Moivre's theorem.
De Moivre's.
Whichever. You can say it the right way or the wrong way. It's up to you.
And we're not telling you which one is which.
Okay. So all it says is we have this complex number in trigonometric form, which is what we've been talking about.
And remember, trigonometric form is really a great way to do a lot of things.
Yeah, we just did multiplying, we did dividing, and it was really easy.
Super easy.
So now if we want to do the complex number to some power, then there's this formula for that you take the r and put it to that power, and then you multiply the angle by whatever
the power is. And I mean, it doesn't get any easier than that.
Can we think for a second?
No, we can't think.
Never mind, I didn't ask. We will think for a second about this. What if we had to do 2 plus 6i to the 5th power?
Without a calculator?
Without a calculator, that's ridiculous.
Good luck.
You have to FOIL, distribute, whatever you want to call it.
A bunch of times.
A bunch of times. Yeah. You'd be really unhappy with us. Nobody wants that. So instead...
That could be the test question. That's how long it'll take.
Yeah. And so instead we can do this formula if we have it in trig form. It would be easier to change this probably to trig form and then use the equations.
Right.
So we're gonna...
And you still could do that without a calculator. But once you get that problem to trig form, you could do it in a matter of minutes instead of a matter of hours.
Right.
Yeah.
The first thing then that we have to do here is we have to change this into trig form. So... our R. We do 1 squared
like a pirate.
plus 1 squared square root and get square root of 2.
Square root of 2, I.
No, not I.
R.
No, not R. And then cosine theta. Now, if you're thinking about this, we have this point 1 comma 1.
Please know what this one is.
1, 1. Oh, we just found out it was square root of 2. This is a 45-degree angle. Now, do we want 45 degrees or do we want radians, or does it matter?
I don't think it matters unless it's something in the directions like between 0 and 360 or between 0 and 2 pi.
Okay, and also keep in mind we're changing it to trig form, but we're going to change it back to standard form, so it really doesn't matter at all. Bless you.
Wow. Excuse me.
It really doesn't matter at all which kind of angle you use there, because you're just going to end up evaluating it.
And they're both going to be the same, so...
Yeah, so we're taking this, now that it's in trig form, to the 5th power, and De Moivre's theorem tells us that that means it would be the square root of 2 to the 5th power.
Right.
Cosine of 5 times pi over 4, which is 5 pi over 4. 5 times pi over 4.
Yeah, according to De Moivre's, it is 5 pi over 4, yes.
Yeah, and then sine, and these angles are always the same. You only have to really do that math once.
Just once.
So this
if you do your math on this and you get an angle for cosine different than the angle you get for sine,
you did something wrong.
There's a mistake.
Yeah. This is trig form. We could simplify the square root of 2 to the 5th power.
Sure.
And I'm going to write it out, but just think about it to yourself, and you'll probably get there pretty quickly. We're saying that we have this kind of situation going on. Well, these two make 2. These two make 2, so that's 4 square roots of 2.
That's
right?
pretty easy.
Okay.
So easy a pirate could do it. Arr!
Yeah, totally. And we want this to be in standard form, which means we need to actually distribute. But check the instructions when you're doing this. They may want you to leave it in trig form, and that would mean that we were done.
Right. So from here, there's a couple different things that we could do to totally clean up the problem and be uber nerdy.
Yeah.
One is we could distribute like Mrs. Stevenson just said. The other one is that we could convert what the sine and cosine at 5 pi over 4 is and multiply that with 4 square roots of 2.
Let's do that.
Let's do it. Okay, sounds great.
Cosine of 5 pi over 4.
Negative square root of 2 over 2.
Okay. And how did you know that?
Well, because it's in the third quadrant.
Well, but like, how would they know that?
Well, because 5 is bigger than 4, and if you have 4 pi over 4, that's 180 degrees.
Right.
So you're pi over 4 units past that.
Is it on the unit circle?
It is on the unit circle.
Okay. So that's another option. You could look at the unit circle.
You could.
The sine of 5 pi over 4
happens to be negative square root of 2 over 2. For all of the same reasons.
Right. Okay, so we have to distribute 4 square roots of 2 to both of these. Well,
square root of 2 times the square root of 2
is 2.
Yep. We just ascertained that.
Okay. And 4 over 2
is 1/2.
No, it's 2.
Right.
So that's 2 times 2, which is 4. That's negative 4. 4 square roots of 2. Oh, that's pretty much the same thing.
Hey, minus 4i.
Yeah. So
look, we could have done 1 plus I all the way out 5 times, or bam, switcheroo, bam, done.
Yeah.
That's what it is.
Yeah, that's what it is. Now, we did something to a power, but we could also
do something with a root.
Yes. So the nth root of a complex number. This top part is talking about nth roots of unity. That has to do with if z equals 1, which is a unit, right?
Complex number z, right?
Yes, complex number z is 1, which means it's really 1 plus 0i.
Right.
Remember, that's a complex number. We'll have some problems where we have to find the nth, like the fifth roots of unity or whatever. And so they're talking about finding like the fifth root of this complex number.
Right. What times what times what times what times what is 1. And we've told you all these years the square root of 1 is 1. Well, maybe we lied.
Maybe. I hope not.
Me too,
because
lying's bad. It's in the 10 Commandments.
Yeah. So we'll do that in a second. Just in general, though, finding nth roots of a general complex number. This is our complex number in trig form. We use this formula right here, which is a little bit on the complicated side.
But we're going to assign almost all of those variables value, and once we substitute in those values, we'll be off and running, and then it cleans itself up quite nicely.
Yes,
actually.
Yes, it does. Keep in mind we're finding the nth root, which means that we'll know what n is. Like if we're finding the cubed root, then n is 3. That's this problem, example 7 we're about to do. So n is 3. Okay, because we're trying to find the
By the way, if
root.
you're at the bottom of your page when you do this, you may need to find some fresh space, because these can
well, I left space,
grow
but somewhere in this general area there is a page turn that you want to make sure and turn the page.
Right. Okay. All right.
You know, that kind of thing. So n equals 3.
Okay. So n equals 3.
The other thing in this besides r, well, we could say what r is. R is 3 as well.
R is 3 because it's the number in front, and then theta is there you go. Theta is 4 pi over 3. Okay. Now k is going to be 3 different things, but it's not going to be 1, 2, 3. With k, you actually have to start with 0.
Yeah, that's what this part right here is saying. We start with 0.
And we go up to n minus 1. Well, if
n is
3, then 3 minus 1 is 2.
And so one way that will help you out is if we're finding the cube roots of it,
you should have
3 things. Okay, because there are 3 different things that end up being the cube root of the complex number.
Right.
Okay. So we plug into this formula right here.
Plug it in.
The third
root of 3. Now, while Mrs. Stevenson's writing all this stuff down and plugging we now know what all our variables are. So she's going to fill in all of this stuff. Right there in the front where it says the cube root of 3, please do not write a decimal. That is going to be incorrect, okay? This is a situation where we want an exact answer only. The formula they give us is the nth root of r. They don't give us an equivalent approximation, blah, 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 whatever. So we just leave it as the cube root of 3, and there isn't one that we know of right off the bat that's pretty, so we just leave it that way, okay? Then very, very, very carefully fill in the rest of your stuff. Now, right here, k should be 0 since this is our first.
Well, I was going to do a little what if kind of situation.
Oh,
what if we
some
simplify? Here's something I like to do. I like to go ahead and simplify this where it's k, and then it'll be easier to plug in 0, 1, and 2.
Whatever you want to do,
If right now we
Steve.
plug in 0, 1, and 2, 0 will be pretty easy, but 1 and 2 require common denominators. If we just go ahead and simplify it right off the bat, then we'll only have to do that
Let's
math
do it.
once.
Let's do it.
So
Let's simplify. I like to simplify. It's
come up
good for
here.
me and builds character.
4 pi over 3 plus, now we want a common denominator of 3. So 2 pi over k right now, it has a denominator of 1. We want it to be 3, so we times the top and the bottom by 3 and get 6 pi k.
So this is exactly like adding the fractions up from when you were a child, except these fractions are quite nasty.
Well, yeah.
I mean, but the process is the same.
So they have a common denominator, so we put them together on top. 4 pi plus 6 pi k. Notice that those are not like terms because one of them has a k and one of them doesn't. And then 3 on bottom here is like 3 over 1, which means we flip up and multiply
Just like you learned how to do in, like, I guess 5th grade. Rowan hasn't learned it yet, so it's going to be a 5th grade deal, I guess.
Okay.
He's in 4th grade. So.
Or later, whichever.
Yeah, you know.
So the numerator will be over 3 times 3, which is 9. Now that we have this is what we're going to plug 0, 1, 2 into.
And that's what becomes the inside part of our cosine.
Yeah. So if k is 0, then we have the third root of 3 times cosine. If we put in a 0 here.
4 pi over 9.
Right, because this will go away, so we'll just have 4 pi over 9. And if you're having problems with that, actually write it out with 0 and then see what happens.
And look at it. And again, you should have 4 pi over 9 in both places for both trig functions. If you don't, then there's a whoops somewhere along the way that you're going to have to locate.
We only did this once because we know these have to be the same.
Yeah, they've got to be identical.
Okay, so k equals 1. We still have the cube root of 3. And now we need to think about if
So if I put 1 in there, I'm going to have 4 ply.
4 ply?
I got some floor ply. I got some floor ply saran wrap. You need 4 pi plus 6 pi, which is 10 pi over 9.
Did you say 4 ply saran wrap?
Yeah. Is it 4 ply Reynolds wrap?
Does saran wrap even have ply?
I don't know.
Okay, 10 pi over 9. That's not.
That's a pi.
That's a pi.
10 I like pi.
Pi over 9 plus I sine 10 pi over 9. All right, that's when k equals 1. Now we got to do k equals 2.
So now you're going to substitute in the 2 for the k, and that's going to be 6 times pi times 2, which is 12. So 4 pi plus 12 pi.
That's a tough one. Do you think
16 pi, I think?
Times
Yeah,
6,
it's
12,
12, 16,
12
16?
16 pi.
Yeah, I like 16.
Okay. 16 pi over 9 plus I sine 16 pi.
This is your cube root of the complex number 3 cosine 4 pi over 3 plus I sine 4 pi over 3. Now, do you want to know how you can check yourself real quick? There's a real quick, easy check to see if you've kind of gone the right direction.
Okay.
Well, check it out. We started with 4 pi over 9, right? Mm-hmm. Then we got to 10 pi over 9, mm-hmm. right? And then we got to 16 pi over 9, right?
You know, I noticed that those are 6 pi over 9 apart.
If you do your math correctly,
that should happen.
Between 0 and 1, then you know what to add every single time.
Yeah.
And you know what happen? You know what happens if we add 6 pi over 9 to 16 pi over 9?
We get 22 pi over 9.
Which
is 4 pi over 9.
There you go.
Subtract 2 pi.
That's correct. And so now we're back to where we started.
Amazing.
Amazing indeed.
Okay.
Find the fifth roots of the complex number 2i. And so we're going to take the exact... Wait a second. There's no plus b. There's no...
Is this what
Thank
you're getting at?
goodness that you wrote that down. I was getting lost.
In standard form, if we want both parts, it's 0 plus 2i, which is...
Oh, I already know what r is.
Yeah, what is it?
2.
That's right, because our point is up here at 90 degrees. Oh, that's helpful, that it's at 90 degrees.
Wow, 90.
Yeah, or
Pi over 2,
pi over 2.
perhaps?
So r is 2, because that's how far it is from 0. You can do the Pythagorean theorem on it, and it'll still tell you it's 2, unless you screw up. Theta is pi over 2.
So please don't screw up. Heaven forbid you become a screw up. Which will be what you are if you screw that up. You just called them that.
No, don't put words in my mouth.
N,
it's the fifth root, so n is 5, which means that the values we're going to plug in for k are 0.
Always start at 0 for
1,
k.
2, 3, 4.
How many k's do we have there,
We
Mrs.
have
Stevenson?
5 numbers
There we
because
go.
it's the fifth root.
Fab-tabulous.
Okay, so our formula says in the nth root of r, so the fifth root of 2 times cosine of, I don't suppose you have the, oh look, you have the formula handy. Pi over 2.
I happen to have the formula right here so we can, use
Plus
it if we need.
2 pi k. And then on bottom, we have...
Fiver fever.
Did you just say Bieber fever?
No.
No?
Fiver fever.
Oh. Thought...
Why would I have Bieber fever?
I don't know. I was going to be concerned. I'm not going to lie.
Maybe I'll put Bieber fever in our tags on YouTube and see how many hits this video gets.
That's terrible. So we need a common denominator. So that we'll have to times by 2. So that's 4 pi k over 2
over 5.
So
hey, look, the denominators on the top are the same.
Yeah.
That's nice.
Last year when I made this video, I totally messed this part up.
Good thing
I
I'm here to
remember-
make sure that you don't mess it up.
I remember because when we multiply by 1/5, we get a 10 on the bottom.
10 down there.
So I screwed that up last year. I feel really bad about it.
And you just admitted your mistake on...
Well, I'd already admitted it on YouTube.
Yeah, and
So-
you're going to admit it again? You
Well,
don't like to
it's-
admit mistakes.
Hey, everyone makes mistakes. I don't like admitting my mistakes
When
to
you
you because you
so-
gloat about it. Okay, if we plug in 0... Okay, if we plug in 0 for k,
You're going to just get pi
right, if
over
we
10.
put a 0 here, 4 pi times 0 is 0, so that's pi over 10. I don't know what's happening
What
with
is
this line.
happening? Get that line out of there.
Okay. Pi over 10.
Plus I sine pi over 10. Now, if we do our math correctly, we only need to do one more.
And then we'll just
And
be able
then
to
we
look
will
at
know.
the pattern.
Yes.
So let's be careful. K equals 1. That means we have the fifth root of 2. Cosine.
And then you're going to have pi plus 4 pi over 10.
Absolutely. So pi plus 4 pi is 5 pi.
Over 10.
5 pi over 10. That reduces.
I know
Are we
that
going to leave it
reduces.
as 5 pi over 10?
Well, let's leave it as 5 pi over 10 for just a second, and then we can be uber cool and reduce.
Uber cool and reduce.
Yeah.
Okay.
So how far from pi over 10 to 5 pi over 10, K. Steve?
If you have problems visualizing that, you just would subtract the second minus the first. They are 4 pi over 10 apart.
So we can add 4 pi over 10.
And get the rest of these.
And get the rest of these.
Yeah. So when k equals 2, we should get the fifth root of 2 cosine
9 pi over 10. Look, we said it together. Jinx, you owe me a soda.
Okay.
And my daughters like to add a Barbie doll after that when they do that. Jinx, you owe me a soda and a Barbie doll. they
That's
say.
funny.
Yeah.
Add 4 pi over
13 pi over 10. Wow, that's
Just
like a...
don't worry about that
It's
I.
an eye in the wind there. It's being blown.
K equals 4, that's our last one because it gives us our fifth root.
And 4 plus 13 is 17.
Yep.
17 pi over 10.
plus I sine.
Now, if you are turning this in as a completed problem, you might just check with your teacher to see. I think for us, we're comfortable with 5 pi over 10 being in there.
Because and partially because of the relationship here that these are a pattern.
Right.
If it wasn't for that, then yeah, definitely simplify. But because in some ways this is easier to look at because, oh look, they're all 4 pi over 10
and look,
apart.
they all kind of slant a little bit further to the right.
Yeah, that's me. That's not on purpose.
Okay.
That's me writing. So.
But some teachers like to see reduced fractions in there, in which case this would just be pi over 2, and that's not a hard thing to make.
Yeah. Now, also, we could convert these to standard form.
Yeah.
Just like we've done anything else, and then we could look at the at those actual points.
Right.
And I mentioned this because it's like, well, normally, like, okay, the cubed root of 8. For example, is 2.
Right.
That's a number.
That's a specific one. That's one we can work with.
Yeah.
Like if.
So how did I just get 5 different things whenever I found the 5th root of this?
Well, what this is telling us is that you're going to have to multiply this specific number 5 times to get back to where you started.
Multiplying all of these together gets back to where you started. But it also has to do with if we graph these, like pi over 10 with that radius. So that's a very small amount.
They space themselves out
and then up
perfectly.
Here, and then 9 pi over 10, and then this is tricky 13 pi over 10. And what should happen is it should look like those are all equidistant apart, and that's why we're multiplying the same thing
each
together 5 times.
Right.
That's the root part of it.
Right.
It's just a
that's
little.
how it works.
It's a little different for complex numbers than what we normally think about.
Right.
So.
Right. It's really interesting.
Yeah.
Yeah. There's no yeah.
Hey, example 9.
Roots of unity.
Unity. We started talking about this earlier. That we're talking about the 4th root of 1. Right?
What times what times what times what is 1?
Exactly.
Yes.
And so but the reason that it's not just like an answer of 1 is we're going to graph each root in the complex plane. It's going to be similar to what we just did actually at the very end of example 8.
Yeah.
So if we're talking about 1, that's 1 plus 0 bi.
By the way, I think this is really neat how this works out.
I. Yeah. No,
honestly,
totally.
I think this is pretty cool.
Yeah.
Because who knew?
I
never did.
Someone did.
I mean, geniusy.
1 is over here.
So r equals 1. Theta will be 0. R equals 1.
Yeah, that's totally what I meant. R equals 1. Theta equals 0.
And in the fourth root of unity, so that n is 4, and k is going to be 0, 1, 2, and 3. There's a comma there.
Yeah, this is not my writing day apparently.
But your writing day is your bad writing day is better than my best writing day. So
I'll just keep going.
Indeed.
So the 4th root of 1,
which we know, by the way, and we'll clean that up in a second.
Okay, and cosine of
0 plus
2k
2 pi
k over 4.
Yes, indeed.
All right. So that's really nifty that that's a 0 there. I feel like that's going to be super helpful.
I mean,
somewhat
could be worse.
Well, for one thing, we don't have a fraction on top.
No,
so
we don't have to worry about it. So that's the guy. 2k pi over 4.
2 pi k?
What?
2k pi. Whichever way.
Commutative property of multiplication means that I can say it how I want to, and you can say it how you want to, and we can both say it differently and be the same.
The 4th root of 1 is
1.
And so really, do we even need to write 1 parentheses?
I mean, not in this case, I don't think so.
Do you want me to leave it as 1 parentheses?
It's up to you. You're doing the writing today. I'll let you make those big decisions.
Okay, well, if I plug in a 0 here, I get 0.
Oh, so hey, looky there. By the way, we can do that. The cosine of 0 is...
Cosine of 0 is 1.
The sine of 0 is
0, which makes this 1 plus 0 I.
Hey, that's...
Which is just 1.
That's 1. That's where we start. Okay, k equals 1. Now this is where it gets really fun and exciting. Okay? Because now we're going to have 2 times... who was that kid?
It's one of my students. 2 pi over 4 times 1. So that's 2 pi over 4.
Which is pi over 2.
Pi over 2.
Plus I sine pi over 2.
Hey, we can figure out what that is.
That's going to be 0 and 1.
Yep, just go right around the unit circle. So 0
I
plus
smell
1
a pattern.
I. K equals
I'm going to take a stab at what's going to
2?
be next. I'm
Okay.
just going to take a guess. It's
Like
going
the
to
standard
be
form?
-1 plus 0i.
Okay,
Yeah.
because
now when you do 2k times 2, that's 4 pi over 4, which is just pi. And everybody knows the cosine of pi is -1.
Everyone. That's general knowledge.
General indeed.
And sine of pi is 0.
Yes, that's also general knowledge.
And k equals 3.
I'm just going to guess that it's going to be 0 and -1i.
Okay.
Just guessing. Why?
Okay.
Why do you
We
ask?
put a
Why?
3.
Why do you ask? Why?
Why do I ask what?
Why do you? Because 2 times pi times k in this case is 3, so that's going to be 3 pi over 2.
Okay. I'm not sure what just happened.
Math happened. Math is happening right now.
No,
Look
in the conversation that we just
Math
had.
happened in that conversation.
Cosine of 3 pi over 2.
0.
0. Okay. And sine of 3 pi over 2.
See,
-1.
-1.
That was a close one, actually. I almost screwed that up, but I didn't. So
thank
now
goodness.
what happens if we graph this? Now we've got 1, 0, which is here. We've got 0, 1, which is up here. -1, 0, 0, -1. Look at how these are all equidistant apart. They're all 90 degrees apart. Okay, so that's what should happen. If it's the fourth roots, they should all be, there should be 4 things going on here that are all equal.
That are all the same distance.
If it was the third roots of unity, or even third roots in general, I guess. Well, the third roots of unity, you'd start here again, right? But then you're dividing the circle into thirds. So over here and over
down there
here.
somewhere, yeah.
Okay, because that's dividing a circle into thirds.
That's a great circle.
Totally. That's the best circle ever.
But this is really a cool thing. And so if we ask you to do like the 8 roots of unity, it really shouldn't be a problem once you get the first one.
Yeah. Well.
The second one.
Yeah. Because this one worked out really nicely because they were on the
4s,
quadrants,
yeah.
But otherwise we might have wanted to use the pattern
that
they were all pi over 2 apart.
Right.
Or actually, we could have used the pattern in that.
Yeah.
Whichever.
Indeed.
Hey,
kids, we were talking about,
But do you have one?
You first.
Well, I was going to say, because someone requested this as a code word, and it's taking me a really long time to do it. So, code word today is totes jelly.
Oh, that is, I love that code word.
Yeah.
I'm totes jelly. That's what the code word is.
Code word is totes jelly. If you tell us that you didn't find the code word, it's because you didn't watch the whole video.
Totes
Now we know.
jelly. Ooh, the whole video. Darn